Okay. Yeah. Thank you. Yes. So I was trying to run a few samples, which like uh, you all accessed the virtual lab. You all could go through it.
Yes. Ma'am, can you increase the length of this terminal?
Hello. Can you be a bit louder?
Can you increase the length of this terminal because I'm not able to see the right hand side.
Okay. The length. Is this better now?
It's better now.
Okay. Yes. So you understood the first instruction. How do you know which GPU you have, or what are the what is the current state of this GPU you should use? NVIDIA SMI. Okay. So the GPU here is Tesla T4 GPU. So if you search about this Tesla T4 GPU, it's a data center GPU which is designed for AI machine learning kind of tasks, and it has around 320 tensor cores and 16 GB of GDDR6 memory. Okay, so now moving on. Uh, Here you can also check what is its power consumption, which is currently 24 watts. The cap of power is 70 watts. Then the temperature also you can see of this GPU here. It is 27 degrees currently, well cool. And if there are any processes which are running on the GPU, it will be shown here if you do NVIDIA SMI when the process is running. The CUDA version which is available to you on this is CUDA 12.9. Now, how do you get the NVIDIA? How do you run a CUDA program? So as you can see here, I have created a vec.cu file here, which is a simple vector addition code. Let me just open it and show it to you. In this code, you have a global function, which is your CUDA kernel function. The name is add vectors. In this, you take the ID of the thread, and once you get the ID of this thread, you just add two arrays. So each thread will add these two different arrays A and B and store its result in the C array. In the main program, we first create the number of bytes that we need to allocate, what is the size we need to allocate, depending on what is the number of elements. Then we allocate three arrays. These three arrays, as you can see, are allocated on the host. Okay, so these are for the host. So you can either have ABC or you can do H underscore A, H underscore B so that you know that these are host arrays. Then you allocate them on the host, that is on your CPU. Next, you allocate the memory for arrays on the device. That is, you first declare the device pointers D underscore A, D underscore B, and D underscore C. Then you do CUDA malloc for all the three arrays. And then you first initialize these arrays randomly with some numbers. Next, you will copy this the host array, that is this array A, to device by using CUDA memcopy functions. So here you mention the device array, the host array, the number of bytes you are trying to copy, and what is the direction in which you are trying to copy. That is, in the first case, it is CUDA memcopy host to device, and for B also, we are copying from data from your host, that is from your CPU, to your device, that is your GPU. Now, you have to decide what should be your launch parameter. So we will be discussing in more detail how you choose the launch parameters, how you calculate the index of each thread in a in your kernel. But for this example, we have chosen the threads per block to be 256. Now we calculate how many blocks of thread we have in this grid. To do that, we have used a formula where we are dividing the total number of elements by the threads per block. Okay, so this calculation is depends on you how you want to calculate the number of blocks in your grid, or you want to give a fixed number. So this helps In case if you want to increase the if you just increase the n, you don't have to then now bother about this change of thread and block grid, because it is related by a formula which is related to n. And that's why having a formula for, at least for the calculating the grid size, that is how many blocks are that part of the grid, helps. Next would be, now that we are ready, we have moved the data from your CPU to a GPU. We have chosen the launch parameters for our kernel. The next task is to launch the kernel. So here we are providing how many blocks will be in the grid and how many threads per block will be there. We also mentioned the array that we need, d underscore a and d underscore b and ds underscore c. Next, now once we launch the kernel, there multiple threads will be spawned on your GPU. They will do the addition on your GPU, and once they do the addition, you then have to copy your data back from your CPU, sorry, back from your GPU to your CPU. So here you add a CUDA mem copy. So this CUDA mem copy will copy the C, which is the output array, device this d underscore c to your C. You mention the number of bytes you want to copy, and the function here or the argument here is CUDA mem copy device to host, because you are copying from GPU back to your CPU. Now you are verifying the results. Once the results are verified, you can free your CPU as well as GPU memory, because now you do not need that. And then you can mention the how many threads per block and blocks per grid used and exit. So this is a simple vector addition code. So let us run this code. To run, the compiler that we use is NVCC. If you are trying to, if you type NVCC in your terminal, okay, if anyone of you are trying, if you get an error that NVCC is not found, remember you have to export the path. Okay, so for that, if you simply search, you will get what path should be exported. Okay, or you can add this to your bash RC. Okay, be assured that the CUDA is available to on your machine. And how do you check if CUDA is available on your machine? Is you check your user local on that machine. In user local, if CUDA is present, that means CUDA is accessible to you. CUDA is installed. Okay, CUDA is usually in user local on Ubuntu. Now, moving on, we will compile on VCC the vec.cu. Some warning.
And ma'am, your console is not visible. Can you clean the things? And
Okay.
it's going beyond the.
Is this
Yeah,
okay?
yeah, it's clear now.
Okay. So NVCC vec.cu. Okay, it's compiled. Now we can execute it. and it has executed successfully. Number of elements were these many. Threads per block were 256 and blocks in this grid were 4096. Okay, so this is how you can run a CUDA program. Create one in your you log in on your this virtual lab, check which GPU is available to you, create a CUDA program by creating a .cu file in your home. Once you create the .cu file, compile it using an ECC and execute this code. You have,
Then,
if you want to,
then, then during compilation, we get the warning, like software for offline compilation. That is ignorable.
is anyone saying something?
Yeah, hello. Can you hear me
Huh?
now? Yeah.
Yes.
So during compilation of we use the NVCC command, so we got one warning. Support for offline compilation. So that warning could be ignorable.
Sorry. Somehow I'm not able to hear you. Uh, there is a bit of noise. Can you, yeah, can you please repeat or type in the chat?
Okay. Is it now? Then audio.
Yes. Or maybe just give me a minute. I'll change my headphones. Maybe I'm using new headphones and I'm not able to hear.
No, no,
So,
ma'am, it is a problem for
It's
all of us.
yeah,
It
it's
is
the same
problem
for
from,
us.
yeah, his side, not our side.
okay.
Ma'am, meantime,
Yes.
can you
Yeah.
open up the program one more time?
Yes, sure. Yes.
Uh, I missed last lecture. I listened the recording for that. Here
Hmm.
we are not synchronizing, right? Once
Yeah, here, yes, we have to synchronize.
we have to, right?
Yeah. Synchronization is important. There is a possibility that the CUDA mem copy might happen before the, you know,
Right.
yeah.
Actually, all
Synchronization
threads.
is important. Yes, it is important.
Right. And how do we know correctness of this program? As in, how do we verify the result?
So, in this case, for verifying the result, uh, they have used,
Greater than
um,
tolerance. Okay.
yes,
Okay. So we are checking whether C of every element of C of I has to be
hmm,
3.0. If it is
yes,
not,
hmm,
if it is not, then there is a problem. Okay. I thought
problem. Yeah,
if we can print that as a number of elements are too high though, that's another
okay.
problem.
Mm-hmm. Let me just check how the same solution is implemented in CUDA samples. Let me.
Yeah.
mm, so I have also cloned the CUDA samples here. Uh, CUDA samples. If you just uh, search for clone CUDA samples, because earlier they used to come directly with CUDA toolkit, but somehow now they expect you to clone if you want to go through them, and this is the git clone command that you get easily if you just Google. And then with this, you can clone the CUDA samples. So, sorry, let me just go back to the lab. Yeah, terminal. Um, so here I have cloned them, and In CUDA samples, you have thousands of CUDA solutions which are already implemented. So if you go to series samples, hmm, um, introduction, here there is a vector add. As you can see, there are many. Right. So
Hmm.
I'll just clear this. Let me do ls again. So many of them are there. There are many others in the other um, very interesting applications in the other folders as well. So we go to vector addition. So you have a readme here. Want you can go through this readme. Okay, let us go through the vector addition code. The CU here, which is implemented by NVIDIA, where yes, there is a lot more. Like I did not show this first because there is a lot more that they have.
Hmm.
Like this is well written, so you can go through this to see what you should ensure in order to write a good code. So yeah, here I think earlier part is copying the data from host to device, and now here is where we are launching the kernel. The threads per block are 256, blocks per grid are calculated here. Then we launch our vector addition code kernel, and here um, they have
Okay, even they have not done
they
synchronization
have
yet.
not used synchronization, but they are checking CUDA get last
Error.
error here. Yeah, so I think that takes care of the and ensures that it's complete. Then they copy the device array to host array, and again they check if this is complete or not. Then they verify here the results by checking. Okay, here they are
Similar.
checking if
Hmm.
yes, similar.
Similar way they've done it. Similar way
Yeah,
only.
yes, yes. And then they say pass the this is complete, and then they free the memory.
Yeah. Yeah. If you can scroll up, ma'am, one question there.
Where?
While computing the block, no,
Okay,
no, no,
sure.
no. You went two up, maybe at the
Yes,
middle.
yes. So here I think it is. Mm,
Albanyama.
okay, here.
Yeah, yeah, here only, here only. Here we
Hmm.
specify threads per block as
Hmm.
256, and then we
Hmm.
compute blocks per grid.
Hmm.
So number of elements plus threads per block minus 1 divided by threads per block. That minus 1, why do we do minus 1 over there? Any specific reason?
Hmm. This is
Why do we?
because
Mhm.
yeah. So uh, if we have 256 threads per block, we need the total number of elements plus thread blocks. Um, so minus one will ensure that anyways it is number of threads, number of elements by thread blocks, right? This minus one, um, minus 1, how does it help?
Exactly. I was wondering about that.
Because it's an integer value, so it will always not use it because it will be always number of elements by thread block. How will this help? Hmm. Yeah, this is like a good observation. Why did they do it? Okay, yeah, let me think about it after the class and I'll get back to you in the next class.
Yeah.
So,
One more thing. If you scroll
yeah,
down further,
yes,
at the end we release the memory.
yeah,
And then typical memory, as in the host memory, is freed up at the end, h underscore a b c.
yeah,
And
yeah,
then for freeing the CUDA based memory, we are doing CUDA free. Now,
yes.
assuming we allocate memory in CUDA and we don't release it,
Hmm.
what would happen?
So, if yeah, so if we allocate the memory on the device
Hmm.
and if uh, we do not free it, okay, then you will it will remain allocated. Maybe it will get erased. Yeah. So this is quite similar to how
చెప్పండి.
our basic malloc works, right? So uh, if we so what will happen that memory will remain occupied until our application will terminate. And in case if our application runs for some longer period, or if it repeatedly allocates some memory without freeing, then it will obviously cause some memory issues. Like
ఏం
these
చేస్తున్నారు
memory
ఫోన్
leaks can slow down the application or it might crash the application, right?
ఏమంటుంది
And in case if your application consumes all available GPU memory,
కదా
then other applications or other processes may not be
ఏముంది
able to function properly also.
ఆహా
True, true. That would happen. But
Yeah.
importantly, see, if we consider the last part, h underscore b, h underscore c,
Hmm.
now that
Hmm.
memory is allocated on CPU,
నేను
Yes.
ఇప్పుడు
host machine. So
చెప్తే
host
ఏమైందమ్మా
knows
Yeah.
that this memory is owned
ముప్పై
by
ఆరు
me.
Yes.
పెట్టేసరికి రెండు మూడు
Can you
వేలు అయిపోయింది
mute others? I'm not sure. Like we are
అడ్వాన్స్
seeing
పెట్టేసరికి రెండు మూడు వేలు
I
అయిపోయింది
think,
there is a disturbance from one of the.
yeah,
ఇట్లా
a funny Bhushan. I think you have not muted your, or let me mute him. Okay. Yes,
Yeah,
you can continue.
yeah. So
Yes.
host memory and device memory, those two things are separate. So host doesn't have a control on what is allocated or deallocated on device that way, right? We have to do
Yeah.
it through CUDA call.
Yes.
Now, typically, if we allocate memory and we do not free it, it remains occupied till the time program is executed, and at the end, once
Hmm.
program is terminated, the memory is freed up and OS reclaims it. That would happen
Yes.
for memory allocated on host. But if
Yes.
we consider memory allocated on device is not in direct control of host. So program gets executed on host machine, it gets terminated there, and memory will be claimed for host based memory allocation.
Hmm.
But if we don't do it for CUDA based memory allocation, then I wasn't too sure like how host machine will take over device.
No. So once the kernel function is over, the kernel function terminates from your device. The memory that was used will get kind of this
Freedom.
once the CUDA program completes, it will get freed up. But
Okay.
what if it works for a longer, like
Right.
continuously
Longer
for a
time.
longer
Right.
period?
It
The
would be a
memory
memory
leaks
leak.
basically.
Yeah, it
Yeah,
would be a
memory
memory
leaks.
leak, and we won't be able to use that memory
Yeah,
until
yeah.
the program finishes. So that
Yes,
problem is
yes.
there. Right.
That is the, yeah.
Right. Right. But because there are two separate notions now, host memory and device memory,
Yes.
I had this question in my mind.
Okay.
Yeah. Thanks.
So yeah. Uh, Continuing our discussion. And let me just close this. So you can download these samples, run these samples, and there are many of them. So as you can see, we have basic matmal. Sorry, we have matmal, matrix multiplication, some simple sorting, and there is one with CUDA OpenMP as well. Uh, then there are some. If you go to utilities, there are some other interesting samples which help you to uh, now device query gives you all the details of your device of your GPU. You can uh, let me see if I'm able to run this. There is no make. Is there a make? So, oops, no, this is CMake list.c. So helper CUDA it needs. You have to link the helper CUDA file here. You just how do we link it? You have to give minus I think my guess is. So you have to provide the path to these samples for the helper files. Let me try that. And we see try. Oh, these helper files is are in common folder of your samples. Let me just first check. Yes. Okay, in samples you have common. Yeah, you have a common folder. All the functions, all these helper functions are in your common folder. So As I mentioned, if you go to user local, you'll be able to see the CUDA installation here. This go. You have these samples in your CUDA home cloud desktop samples. Of common C is capital. Okay, so let me go to samples, utilities, device query. Let me try to provide a path frame. Great. So this is how we can link the path. I'm not able to copy this sample folder in the uh, user local because I do not have the permission. So I have cloned it on the desktop and then provided or linked the path to of the helper function. Clear what I've done? Yeah.
Yes.
So now it's the executable is ready. So this is how the device query looks like. It's a Tesla T4 GPU. The runtime version of CUDA is 12.9. The You can see the clock rate. The GPU clock rate is 1590 megahertz. The memory clock rate is 5001 megahertz. The it has okay. Uh, yeah, I had mentioned about compute capability. This is 7.5 here, which is the architectural compute capability, as in what all can be done using this machine. The total amount of global memory is 1419 megabytes, so around 15 GB we have. The This has total 40 streaming multiprocessors, that is SMs. We discussed this in the last class. I hope you all remember. Each of which has 64 cores. So 40 into 64, we have total 2560 CUDA cores on this GPU. The L2 cache size is around 4194304 bytes. The total amount of constant memory is this. Total amount of shared memory per block we can have is 49152 bytes. Then total shared memory per multiprocessor is this. This is the maximum per block and this is per SM. Total number of registers which are available per block are these. Okay. Then this warp size, I think we'll discuss this in today's class. Then maximum number of threads which can be active at a time on the multiprocessor or on a SM is 1024, and maximum number of threads per block which are allowed while launching the block is 1024. Maximum dimension or size of your thread block that you can launch is this. Sorry. and maximum size of your grid is this. Then you there are few things about what all your device supports. It supports unified addressing, it supports unified memory, it supports preemption. uh, you can have more than one kernel launch, and so many other things about your device you can know from by just running this device query. Clear? Let me just run something else to so
I do have one basic question.
yes,
Uh, is this CUDA only targeted for the NVIDIA
ye-
GPU or it's a
it is
common for?
only for NVIDIA GPU. So, if you want to develop something which is common for other GPUs as well, then you will have to use OpenCL,
Okay,
which is platform independent. CUDA is specific to NVIDIA.
okay.
Hmm. Then let us maybe go to, we can go to the introduction part and run a few interesting benchmarks. Here we can maybe run a basic matrix multiplication. Let us first go through its the code. So this matrix multiplication uses some shared variables. Here we'll talk about what shared variables are, and it is using synchronization for these variables and then doing the matrix multiplication here. And other things will remain similar. Create two matrices, move them to device, then calculate the block size, grid size, and then execute, run the kernel. Once the kernel is run, then they're calculating the performance for this application and printing it. Let us just execute this code and see how it looks. And I think we will have to provide it the helper function. I think it's Pura sample. So as you can see here, we executed the matrix multiplication where the first matrix was 320 cross 320, the other matrix was 640 cross 320. We took 0.319 milliseconds. So Results are correct. If you want to profile and see or know few details about how this application ran, we can use Profiler. Here we can use a NVProf and provide this. Oh, sorry, my bad. So we provide the executable. So this NVProf profiles the application, and here, as you can see, the it shows you time taken for each of the functions. So how much time it took for CUDA malloc, for the host allocation, for launching the kernel, for the memcopy host to device took 100 microseconds, device to host took 124 microseconds, the kernel launch took 320 around 320 microseconds. So NVProf provides you different metrics. Think uh, I think to recollect except no, how do you get difference metrics from so yes, yeah, this is the one I was searching. So it tells you what all metrics you can. Okay, not showing you now. Okay, let's do use this. Maybe just check two of the metrics using NVProf. Let me clear this. So I'm just checking two metrics. Okay, why? Okay, I'll get back to you on this profiling in the next class. Why it is not showing? I'll have to check. Okay. In the meantime, let us run OpenMP and MPI code so that we can move back to learning our CUDA. So I was in home, I think. So yes, so this this is the simple. So this was a simple OpenMP program. And if you want to run an MPI program, it is MPI 60 MPI.c and data out, and you can run this hello world. So here we are using a MPI get processor name, which gives you the name of my current processor. That's why it print that hello from the processor name here, and then the rank and out of how many processors are active. In this case, only one for this particular program. So you can try using this virtual lab that is now available to you. Try running these different programming model problems, which are uh, try first with a predefined pre-written code, and then try playing with and writing interesting codes and executing them here. So let us move back to our discussion on CUDA by taking maybe a 5 minute break, 5 to 10 minutes break.
Ma'am, one question here. Why we are
Yeah.
running here MPIC? That's we are done it long time back. Is there any relation with MPIC and CUDA?
No. I couldn't run MPICC and OpenMP on the virtual lab then because it was not available.
Okay,
So
okay,
I'm
okay.
just
I,
showing
I
that now the lab is available, the compiler is already installed. If you
yeah.
want to try things out, you're free to do it. That's why,
Okay,
nothing else. Yeah, just wanted to show that it is available to you now, and you're free to try it out if you want now because it was not available to us earlier. There is no
okay.
relationship between CUDA and these. So yeah, so let us maybe uh, rejoin around 9:25 and continue our discussion with CUDA.
Okay.
Any doubts in terms of using virtual lab, then you can ask now. Okay, then let us join back around 9:25 and continue our discussion on CUDA. Okay, so let us continue our discussion. I hope I'm audible and my screen is visible.
Yes, ma'am.
Yeah, yes, thank you. So, in the last class, we saw how a CUDA program is designed, but we have not discussed a very important part of designing this CUDA kernel is how do we choose the launch parameters and how these launch parameters help us to calculate the unique thread in ID, which will eventually do the task or work on the finally on the required data. So this is the programming structure that we learned in the last class or even discussed in the earlier session for the with respect to the vector addition as well as the matrix multiplication. So we can have a CUDA application where we can have multiple such kernels, and there will be some part of the code which will get executed on the kernel on the CPU, and some of it will be on the GPU. And if the code has multiple GPU kernels, again some part will happen on the CPU, and then some part will then happen on your GPU. So when you do CUDA malloc, you might either get a CUDA success or you might get a CUDA error memory allocation. Now, how do you choose this grid and block size? So when when these threads are programmed, or when a programmer thinks about these threads, we think in the with the perspective of a block and a grid. A block is a bunch of threads, and a grid is a bunch of blocks per thread. So when this code eventually executes on your GPU, it executes not the in terms of blocks or in terms of grids, but the execution unit is a warp, and a warp is a set of 32 threads. So warp will have 32 threads which will get the same instruction for execution, okay, and will be running the same instructions in every cycle. There could be some branch diversions, but it is supposed to do this task in this group of 32 threads. So when the warp scheduler in your GPU's SM schedules the instruction, it will choose a warp, take a bunch of 32 threads, and then these 32 threads, it will give one instruction at a time. So all the threads in that warp will execute the same instruction. Therefore, when you choose the threads per block size, it is better to have it in terms of multiple of the warp size. Okay, why we will also discuss this in the later slides. Then it is advised to have small block sizes. That is, you can have around 128 or 256 thread per block, because as we saw, maximum threads per SM are 1024,
Ma'am,
right?
excuse me. Can you just explain again what? Uh,
Concept of warp.
yes.
Okay, so let me see if I have the figure of the SM. Okay, yeah. So here, this is a SM of Fermi architecture. Sorry. And you can see, so sorry. Yeah, there is instruction cache where instructions are stored, and there is warp scheduler and dispatch unit. Okay, so when as we have discussed, When we are trying to assign these blocks, say uh, a GPU, let's assume, has 4 SMs. Okay, and you have around sorry 7 blocks to be assigned. So in the first cycle, the first block will go here, second block will go here, third block will go here, fourth block will go here. Then the fifth block will be assigned here, sixth will be assigned here, and seventh will be assigned here. Okay, so this SM, now maybe this block has around uh let's assume 256 threads per block. Okay, so the grid size is 7. That is, we have 7 blocks and we have 256 threads in each block. So when the SM will get these 256 threads, the warp scheduler will then divide these 256 threads by 32. So how many warps we will have?
Six, sorry, eight.
Yeah, somewhere 8, right? 8 blocks. So we'll have 8 blocks, 8 warps. Okay. So now these warps will be available at the warp scheduler. Now some of these warps will be uh, yes. So there will, when these warps, when the thread block becomes active, you know, we try to allocate the resources, and this block is converted to warps, and these warps become the active warps, and these active warps can be of 3 types: selected warp, eligible warp, or stalled warp. Okay, so now depending on how many cores you have, let's say you have 256 threads, there are 32 blocks, right? Sorry, 32 threads in a warp. So you have 8 of these warps ready. But you may have only 64 cores on your asset. So at one point, some warps will be active, which are selected warps. Some will have to wait, who will be eligible warps, and some may have to wait longer because they are not ready to for execution because they are ready waiting for some resource or so. Okay, so that's how these warps wait, and once they are selected, then dispatch unit provides the instruction that these warps should execute. So all the threads in that warp, 32 threads, will execute instructions of the kernel one after the other, but all of them will execute the same instruction at a time, or will be given the same instruction to be executed at a time. Is it clear what the warp is? How warps work?
Yeah, thanks.
Ma'am, there is one more additional question in the same line. Uh,
Yeah,
if we don't configure all these things, is there any default things for that?
we are not configuring warps. Do not worry.
Because
Did you see?
means
Did you see in the
I,
CUDA vector addition code we configured warps anywhere?
we just hard coding 256.
Threads per block we did, but warp no.
If we
There is,
don't, why are we hard coding the threads? Are we configuring our grid in a such a way that based on our programming requirement, we are configuring our grid? I want
yes,
to, okay. That,
yes, yes, yes. And we will see how it is, why it is so. That we are kind of going towards that only. Next slide after this. Hmm?
Okay.
So how
Okay.
do you choose and why do you choose these? Like, see, when you move from your uh, basic OpenMP MPI code to CUDA, you move because you need more number of codes, right? You need more codes, you need more computation. Okay, so if you are doing a vector addition using your OpenMP, on with your CPU, what would have happened is at one time maybe your CPU had 16 cores, right? Maximum 16 cores. So 16 additions would have happened, right? At a time. But when you talk about GPUs has thousands of core. We saw even the T4 has around 4,000 cores, if I'm not wrong. So 4,000 additions can happen at the same time. That's the difference we are getting from here, right? Now, how do each thread know which addition it has to do or how many additions it has to do? That that configuration has to be done using threads per block and blocks grid size. Okay, so we will
Yeah, question
move
here,
on
like if
and
we, ma'am,
uh,
question here, if
yeah,
you don't configure it, we know
uh,
that we have 100 plus GPU on our machines and just do the programming and run the kernels. Is it not going to handle internally?
see, I might have a code here. Okay, so how are you here? Is this is the kernel call, right?
Mm.
So here, if you do not mention grid and block, this will, I think, by default take 1, 1.
Oh, okay, okay.
So only one thread will execute this.
Per block.
One thread or one block. So only one thread.
Okay,
Per block as in because blocks are block also your by default is one.
okay. It's a kind of like serial execution.
Huh. You have to mention.
Okay. Yeah, I'm correlating these things with the grid scheduling, but I think that this is a bit different than the grid scheduling.
Okay,
Means,
okay.
yeah.
Yes. Yeah. So these are some of the guidelines which you can follow when you are trying to choose this grid block configuration. Okay. First is yeah, the block size has to be a multiple of 32. The reason is warp execution happens in the batch of 32. You should avoid small block sizes, that is 16, 32. You should start at least with 128 or 256. Why it helps is if you have such block sizes, then the occupancy or the active number of warps on your SM will always be a good number of warps, and your SM will be always occupied, or there will be some active warps all the time, so that you will get the best performance and there will be no stall cycles. Then you adjust block size because sometimes when you choose a configuration, you may not be able to choose the best configuration, or your chosen configuration may not always give you the best performance or best results. In that case, you have to keep changing, keep trying, and trying out different configurations and observe if you get which gives you better performance. So keep doing that. Then also always keep the number of blocks much greater than the number of SMs, because as I showed you how the SMs get allocated in every cycle, you need more number of blocks than the number of SMs you have, so that all the SMs are occupied and every SM has active warps every cycle, so that you get the best performance. So you conduct these different experiments and discover what is the best configuration and resource usage for your problem. So coming back to organizing the threads. So this figure shows you that grid and block can be organized in either one dimension or two dimension or three dimension. Okay. So, and how do you mention the dimension is using block dim and grid dim. This both can be three dimension. Okay, three dimensional. Now, each block here in this case, what this example is about one dimension, two or three.
We have two dimensions here.
Yes. So this is a two-dimensional example. So let us see how these grid block size are chosen and how you get the unique thread index from this grid block size. So for to calculate the unique thread index, so what is a unique thread index? You may have a 1D grid block or 2D or 3D. Each thread finally will be flattened and each thread will have a unique index. Okay, it may have some index in your block which is common across multiple blocks, but eventually you have to find which thread is going to do the task. So to calculate this unique thread index, you have these three things: thread ID, which is thread index. If it is X, it is in the X dimension. If this is Y, it is in the Y dimension. If it is Z, it is in the Z dimension. Block IDX is the block index. In this case, it is in the X dimension. Again, Y or Z is possible. Block dim gives you what is the dimension of your block. It again can be in X and Y and Z dimension. These three things help you to calculate what is the global thread index for your thread. So, if you want to calculate this global thread index in X dimension, you can compute it as block id dot x into what is the dimension in X, which block in X, what is the dimension of a block, and in this block, what is the thread ID. Okay. So we'll see examples. If it is still not clear, then we can discuss this formula again. So in this example, as you can see, we have this is a grid of four blocks. Okay. We have block 0, 1, 2, and 3. In this four blocks, the dimension of a block, that is how many threads reside in a block, is 8. So each block is a block of 8 threads. Okay. Now, within each block, it will have a block ID, which is in this case is 0 for the first one, second one is 1, third one is 2, and the fourth one is 3. Within each block, there are threads have thread ID, which starts from 0 to 7, right? So 0 to 7 will be same for thread indexes across blocks where the block ID will change. Now, if you want to find out what is the global thread ID of this, and if you want some computation to be done by this thread itself, you will calculate this as block ID dot x. What is the block ID here? Which is, in this case, 3. What is the block dimension? Block dimension is 8. And in this block dimension, what is the thread index? In this case, it is 2. So with this, we calculate that thread 26 is the global ID for this thread in this particular example. Is this clear?
Yes, ma'am.
Any doubts here? Okay. So let us see an example of, if it is still not clear, this example should make things clear. We have here number of elements at 6. The block size is 3. And here we divide 6 by 3, which gives us 2 grid size. So there are 2 blocks of 3 threads each. We are printing grid dimension. We are printing the block dimension. And we are also printing what is the thread index, what is the block index, what is the block dimension, and grid dimension in this particular example. So this looks like a this is the kernel function. So you can go through this for a minute and then we'll see what is the output. So this is the output. So since we have not mentioned what is the x and y and z, by default y and z become 1. Okay? Each thread has a unique x thread dot x for each block ID, unique block ID. Block dimension and grid dimension will remain same for all the threads. Is this clear? So for a given data size, the general step is you first decide the block size. Then you calculate what should be the grid dimension based on the application data size and the block size using some formula. And how do you determine what should be your block dimension? You have to consider what is the performance, what is expected from this kernel, and the limitations on GPU resources. Now, how limitations on GPU resources is related to a block dimension, you might wonder, but it is very important because a block of your code on one SM will be sharing the whole register file that is available to you, and it will be sharing the shared memory. Okay. Now, shared memory requirement of your application will decide how many threads can reside on your block. Based on the requirement of your threads, based on the shared memory requirement and the register requirement of your threads, it will be decided how many threads can reside on your block at a time. So if you need more shared memory, few blocks will be fit. If you need less shared memory per block, more blocks can be fit. So here, as you can see in this example, the number of elements is 1024, and here we change the block size, and with the change in this block size, the grid size changes because we have formulated it accordingly. So first case, we have one block of 1024 threads. In the second case, we have two blocks of 512 threads. In the third case, we have four blocks of 256 threads. And in the fourth case, we have eight blocks of 128 threads. So I hope so far the 1D, at least the 1D part is clear to all. If not, you can, this example show you how the block size and the grid size is directly linked with the indexes of your block and thread.
I have one question here.
Yeah.
How do we know the threads require shared memory or not?
So one way you can find out is at compile time before execution of your code. You have some compile time flags with which you can calculate the shared memory requirement.
Okay. Okay.
Other way would be that because shared memory is what you as a developer have to uh, you know um, declare the shared variables, and these shared variables you will have to then assign value. You will be doing it yourself. You will
Oh,
have fair idea of what each thread will be doing and how much it will need.
okay. I see. We're yet to see that
Yeah,
shared part.
yeah,
Okay.
yes.
Okay. Yeah, that helps. Yeah.
So these are more examples for you to understand how the the thread indexes, the block indexes, and how global thread index is calculated using the thread index and the block index. Now, as I mentioned, we have so far talked more about 1D. Now let us talk about more dimensions or higher dimensions in this grid and block sizes. So we can use this dim3 grid dim with which we can declare three-dimensional grid sizes and block sizes. So number of blocks in a grid will be multiply, you will multiply the grid dim dot x, y, and if there is a z similar for block dimension, you will multiply x, y, and z. So for example, if you have a dim3 grid 16 comma 16 and a block 32 comma 32, the grid size is 16 into 16 blocks and block size is 32 into 32 threads. So if you launch this kernel, the grid dimension will be set to 16, block dimension dot x will be 16 set to 32, and y will be 32. Here the y will be 16, and by default this will be set to 1. Now, how do you calculate the unique thread index in 1D, 2D, and 3D? These are the formulas that you can use to do that. Here, for 1D, we have already seen the formula where we take log idx dot into dim id, dim plus the thread index. If it is a 1D grid, that is only one block of 2D thread blocks, in that case, you calculate the thread index by multiplying dot x into dot y and thread of dot y into dim log dim dot x plus thread index dot x. If it is a 1D grid and 3D block, again the block index will remain unique because it is 1D grid. The thread index will involve calculation of multiplication of dot y as well as dot z to the block ID because it's 3D block. Again, to get you have to multiply the thread.id.x z into block dimension again and block thread id.y into block dimension of x plus thread id.x. For 2D grid of 1D block, the unique block index will be calculated as block id.y into grid dimension.x and plus you have to add the block id.x. The unique thread index will be calculated as unique block index into block dimension.x plus thread index.x and so on. Similarly for 3D grid of 1D block, 3D grid of 2D block, and 3D grid of, sorry, this is I think repeated. So now where we will need such 2D, blocks and 2D dimensions, what are the applications where or 3D blocks where we will need them. So let us see one example of matrix multiplication where we use them. Here we have the output matrix which is C. It has two indices I comma j. Each thread will is linked to one element of C. Each block is linked to a tile, right? So what you can design this problem as each thread will work on multiplying and calculating one element of C, and each block here we can look at it as a tile or a submatrix of this C. The grid we expect to cover the whole m cross n output that we need. So here the hence what we do, we calculate the block dimension to be 16 by 16. So each block will have 16 cross 16 elements of the final C output matrix. The grid dimension we calculate based on how many elements we have in n and m direction. And we launch this kernel matrix mul by using these dimensions, where grid will have these number of blocks, and we will have a 16 cross 16 two-dimensional thread block, which will do the computation for a submatrix of your C. So the code will look a bit like this, where here M and K are the dimensions of the two matrices, and now we need the unique ID of each thread in X and Y direction so that it is able to calculate the matrix multiplication of a single element of your C. So to get it in the Y direction, we calculate the row as block ID x dot y into block dimension dot y plus thread ID x dot y, and column as block ID dot x into block dimension dot x in plus block thread ID dot x. So this way, let's say if this is the block dimension 16, 16, and in this example, let's assume that the grid dimension is 4, 4. The thread, if 2, 3, if it is residing inside this block of 1, 0, row will be 1 into 16 plus 2, which will give you 18, and column will be 0 into 16 plus 3 is equal to 3. It computes C of 18, 3. If it is a thread 2, 3 in, let's say, grid dimension, block dimension 0, 0, it will be, it will compute another C. Each of them will then take, each thread will take elements based on the A and B. For example, if thread 2 of 3 might take A of 2, 0, B of 0, 3, A of 2, 1, and B of 1, 3, and A of 2, 2 and B, 2.3, and it over this for loop add and then assign this sum to the C of row into n plus column. So this gives, we'll write the total to the C of 2, 3. We can, if you want to consider a 3D example,
Yeah, ma'am, one question on the earlier slide.
yes.
Here we say thread 2, 3 computes C of 18, 3.
Hmm.
While below we say thread 2, 3 does writes it to C 2, 3.
No, no, this is the, what is the block dimension here? I said, sorry, I think I was not clear. The block is 1, 0. This thread of 2, 3 is in block of
Okay,
0,
0,
0.
0,
Uh,
0. Okay.
uh,
Okay. Yeah, then it matches.
yeah, yes. Maybe I should mention it here.
Yeah.
Hmm. No. Where you will need a 3D kind of a block is, let's say, let's take this example where we have a cube of metal which is 100 cross 100 cross 100 points, and each point has a temperature. And here we have a 3D grid of temperature values where width will have some number of points along x direction, height will have some number of points along y direction, depth will be some number of points along z direction, and every time step, each point will have to calculate its new temperature depending on its six neighbors, okay, which are left, right, up and down, front and back. So the formula for this new temperature change is something like this, which is mentioned here. This is a very well-known problem in physics, engineering, and some gain engines as well. Anyone is aware of any such application where this is used? Anyone interested in physics might know. This basically tells you how change in one part, change in temperature in one part of the system can then affect the whole system, or the whole system updates temperature based on this change. So we can solve this problem or use this problem and solve it in CUDA by creating a heat 3D kernel where here in the main program we choose the block dimension 888 comma 8 comma 8, and then we calculate the width, height, and depth. With respect to depth, we calculate the grid dimension, the and then kind of execute this kernel and provide the temperature in, out, width, height, and depth. And here we first calculate the XYZ of each block, then calculate the unique index of each thread, and with this unique index of each thread, then we check the bounds of height, width, and the depth, and then use the same formula to calculate an average temperature and assign this average temperature to this unique thread here. You can also look at other examples, and you can maybe try this practice problem where we design a 3D histogram of color intensities. So we have a 3D RGB volume where we have 3D color image. Each one will have red, green, and blue intensity values. And our task is to compute these histograms for the RGB channels. Each histogram will have 256 beans, and you will have to write a CUDA program where it will take this 3D RGB volume of width, height, and depth, and it will use some 3D blocks and grids to parallelize this computation of calculating the histogram. You can use atomic add to safely update some shared or global histogram fields. And in the end, you should be able to produce three histograms, one for red, one for green, and one for blue. So I think I'll stop with this function type qualifiers, and the CUDA execution model we can discuss in the next class. So these function type qualifiers include what kind of functions you can write in CUDA. You can write three types of functions. One is global, which is executed on your device, which is a kernel function. You can have device functions, which are executed on the GPU itself. Now, global functions can be called from your host, that is from your CPU. You can call the global function. You can call these global functions from the device also. It must have a void return type. A device function is executed on the device, but it can be called only from the device, that is only from the kernel function. A CPU function cannot call a device function. Then you have a host qualifier. which is an optional qualifier because this is a CPU function. You may or may not put it. If you do not put it, it will be also by default a CPU function. But these CPU functions are called from the host only. You cannot call these functions from your GPU device functions or global functions. So I think with this, we should stop and we should discuss the CUDA execution model in the next class because it has many more things to be discussed.
Ma'am,
I
one
do
question
not
on this
feel
slide.
this. Yeah, yeah,
Yeah.
yes.
Callable from the device for
Hmm.
devices of compute capability 3. What does that mean?
Okay. Um, so, uh, you're clear about the compute capability concept. What is a computer capability?
Mm, maybe you can summarize that.
Okay, okay. So each each architecture when it is introduced,
Mm,
it comes with a compute capability. So
mm,
this the Kepler architecture uh, had compute capability of 3.5, then
okay.
Max,
Mhm, mhm.
which was I think which came around 10 years back. Then came Maxwell, which was around 4. Then Pascal, which had compute capability of 5. Then
Oh,
came
mhm,
Volta, which was 7. Then Turing. Then Ada Lovelace. There was Ampere also in between. Then now current one, the current new one is the Blackwell architecture. So these are the architectures of GPU which are named by renowned
mhm.
scientists. This is what NVIDIA follows. And with each architecture, it is given a compute capability.
Okay.
So
Okay.
basically, this compute capability represents what all you can do with that architecture. Because with every new architecture, they change the architecture, right?
Mm,
They may
mm,
add some tensor cores, they may remove what seems like absolute and not required now, or you have some better solution to what what was done earlier. So they do these changes in each architecture, and that's how with compute capability, you know that okay, if there is a device with compute capability 3.5, its SM will have a particular structure, a particular organization,
mm,
which will include say number of fixed number of cores, fixed number of special function units, fixed number of load store
mm,
units, and so on.
mm.
So for that, I think the reference from where I took this table, uh, uh, that textbook was written in the era of Kepler architecture and Fermi architecture, and it is mostly comparing the two architecture, Fermi and Kepler. So in
Mm,
the
mm.
Fermi architecture, which was below the compute capability was below 3, you could not call these functions from the device. Okay,
Hmm.
but with Kepler architecture, you this was
Okay.
introduced that you can call these functions from the device as well.
Oh, yeah. Yeah. Get you.
Hmm.
Yeah. And there was one slide wherein we have that architecture explained. Can we go down to that slide
This
where
one,
we have L1, L2 caches? No. No. You showed that up in last class.
okay, maybe
Maybe
I'll
right
have to
at the
open the
beginning.
last. Maybe I'll have to open the last slides. Let me check if it's here or right out. In these slides, we are not discussing the architecture. I think. Let me open the last class. Correct. Is this one?
No, 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 no. Go move further a bit. There was a slide where, which talks about caches. No, not sure. I could see private instruction cache L0 and
No, not here.
yeah,
This,
yeah, yeah. Just hold on.
hmm,
One after this, one after this.
this, or
No, in
this,
between there was one, right? Oh
this,
yeah, this is the one. This is the one. Now, here, if we see, there is a L0 instruction cache
hmm,
with individual unit SM,
hmm,
and there is L1 instruction cache which is shared across them. If
hmm,
we have L0 instruction cache
hmm.
specifically with SM, why do we, like why L1 instruction cache is shared in a way?
See, similarly, you have, sorry, here also, you have each one has L1, but you also have L2, right? It
Hmm.
is because the size of the cache is more when it comes to L1 over L0.
Right. Okay. Hmm.
Okay, so it might so happen that if you fetch some instruction, okay, and you need another instruction, maybe because of some branch divergence, the instruction
Hmm.
that is in L0 may not it may not have the next instruction because of some branch divergence, some branch that you have
Hmm.
taken. You might have to fetch that it from L1 cache, instruction cache, and not go to the main memory for the next instruction. So the latency for L0 will be the least. The
List,
next will
list,
be
list.
L1, and L1 size is more, so it can fit
Yes.
more number of instructions.
Okay. So similar to CPU kind of a
Caching,
concept.
yeah, yeah, yeah,
S-
same concept.
General. There is no change
Yes,
in that thought
no, no,
per se.
no, no, no. It's the same concept.
Okay. And this particularly talks about instruction cache. This is
Mm-hmm.
not a data cache, right?
No, no,
So we
this
have
is
separate
this.
instruction and data caches.
Yes, this is only talking about the instruction
Yeah, it
caches.
is not talking about data cache.
No, see, there is L1 data here.
Hmm.
Data cache is here.
Okay, so all of them are referring to same data cache
Hmm.
in a way, that shared memory
Yeah, L1 data cache and shared memory is shared actually. It's the
shared
same
across all SMs.
memory. It's the same. No, no. This is one SM,
Okay, single
and this
SM
is
unit,
what this is a single SM.
SM
Now,
unit.
before Volta architecture, a SM looked something like this. Uh, here this where
Mhm.
you had them like the shared memory, the codes were at one place, and control was at one place. Later, SM started after Volta. They redesigned it, and now the SM looks like this, where within SM, you know, the codes are divided into separate blocks as well, like this.
Hmm. Okay.
And so this is one SM. The whole thing is one
Hmm.
SM now, post
Hmm.
Volta. Before this looked like one SM, but now this is one SM.
Yeah. Yeah. And then data cache is used across all the blocks of SM within SM.
Hmm. Yeah, within SM.
Okay.
So,
Yeah. That
which is
helps.
this architecture? Yeah. So, okay. Now, can you see here? This, I think, Volta V100. So, you can see here now, this is one SM. And in that, there are these four parts of, codes and other units.
Hmm. Yeah. Yeah, that helps. Thank you.
Okay, then, any other doubts, or we can stop here?
Yeah, I'm good. Thank you.
Yeah. Yes. Thank you.
Thank you.